Hi, everybody. Welcome to my backyard. And say hi to my doggy, Trixie. Trixie! Hi, puppy. Right here, honey. There we go. All right. Today we're going to talk about periodicity. If you have been absent in class, I did hand out a packet that goes along with this presentation, and I might recommend that you get that packet from me before listening to this presentation just because it makes taking notes a little bit easier. Really quickly, the word periodicity, I like to say the word periodicity means patterns. So the periodic table of elements is the patterned table of elements. We can use the patterns that we see in the periodic table to predict what elements exist in the universe. We can also use it to predict how different elements, when they combine, how they will react based on their periodic or their patterned trends. So that's what periodicity is. I'd like to start this by having you sort of make a prediction. There are no wrong answers when you're making a prediction. Along the bottom axis is atomic number. So assume hydrogen is 1. Remember, the atomic number is the number of protons. And then the number gets increasing, goes up and up as the number of protons increases. So we go hydrogen, helium, etc., etc. What is your thought about what would happen to the radius of the atom? So as we increase the number of protons, we increase the number of electrons. So what do you suppose would happen to the size of the atom? And so draw a graph. Remember that this is numbers by numbers. I'm trying to show it with my hands here. It's numbers by numbers. So you would want a line graph. So I'm just going to give you a second to do that because this is a video. And so you can always pause it if you need to. And I'm going to move on. Let's take a look at what it actually should be. This is almost always a surprise to student, what the atomic radius graph actually looks like. So we see a lot of patterns here, and I just want to point them out. It looks random at first, not at all random. The first thing that I want you to notice is hydrogen. You should have your periodic table out, by the way, because it'll really help if you're looking at the periodic table while you're listening to these notes. So the first thing I want you to notice is the pattern of hydrogen, and below hydrogen on the periodic table is lithium, below lithium is sodium, and below sodium is potassium. Notice that they're continuing to get bigger and bigger and bigger, that radius is getting bigger. But in the row that has lithium and it goes all the way through to neon, and I want you to think about what's special about neon, and likewise in the next row, what's special about argon. Well, they're both noble gases. And so what I want you to see is that in the row, and we're going to call the row a period, that'll come up soon. In that period of all those elements that go across between lithium and neon, they're consistently getting smaller, even though we're adding a proton and adding an electron with each element. So lithium has 3, beryllium has 4, boron has 5, all the way up to neon, which has 10. So why isn't neon the largest in that row? Why isn't neon the largest one? And likewise in this row, why isn't argon the largest one? That's what we're going to look for, and that's what we're going to try to solve today. All right, so the next thing on our packet of notes is I'm going to encourage you to try to draw the size of the atoms. I'm going to go through this really fast on the video. You can always pause me as needed. So based on the graph that you saw on the previous slide, we would say hydrogen is a fairly small atom. It's just one proton surrounded by one electron, and it may or may not have a neutron in it. Lithium, however, so hydrogen, is hydrogen in here? Get me out of the way. I don't even remember if I have hydrogen in here. Let's see, is that, there we go, or helium I meant. So helium is there, and helium has a second proton and a second electron, and helium is actually smaller according to our graph that we just drew. So then, I'll move my picture one more time here. Let's see, this is tricky for me. Sorry, I'm trying to move my picture to get it out of our way. Let's try, there we go. Okay, so helium is a little bit smaller than hydrogen. But then on our diagram, on our graph, we saw that lithium was bigger than hydrogen. And then that row got progressively smaller. So what you want to do is draw circles that are getting progressively smaller. However, once we get to the neon gases, to the noble gases, neon is in fact a little bit bigger than hydrogen, just like lithium was a little bit bigger than hydrogen. Oh my gosh, I'm saying everything wrong. Neon is bigger than helium, just like lithium was larger than hydrogen. Now, when we go to the next row, sodium is quite a big atom, and it's bigger than lithium and it's bigger than hydrogen. However, magnesium, the next one, is just a teeny bit smaller. And we want to know why that is, what's causing that. So there's some assumptions that we have to make, and we're going to look at Bohr's model. We know that Bohr's model is wrong, that it's a two-dimensional model, that the electrons are absolutely not traveling around like planets, like orbiting planets around a sun. That's not how it's happening at all. But for the purpose of talking about the radius, about how big an atom is, Bohr's model works. So some assumptions. Number one, there is a limit on the electron's distance from the nucleus. If an electron gets so far away from the nucleus, it eventually doesn't get pulled in by the positive charge of the nucleus and it escapes. So it can only be so far away from the nucleus. There's also a limit on the number of electrons in each shell. We learned that the first shell can hold 2 electrons. The second shell, there we go, can hold 8 electrons. That's because, everybody, remember that electrons are negatively charged. So they don't want to be close together. They're pushing apart like the same poles on a magnet would. And so they're fighting with each other, and you just can't cram too many of them together. So there's a limit to how far they can be, but there's also a limit to how many there can be in any given shell. Okay, so now we get on to what I keep referring to as Mr. Haebel's very questionable analogy. Mr. Haebel designed this, kind of cracks me up. You know what? I wonder if I can. Okay. So Mr. Haebel designed this, and it kind of makes me laugh. So first of all, we're going to look at an atom that has a nucleus that has 10 protons in it. And in his analogy, he's saying that the nucleus is very attractive, and that the electrons around it are attracted to this very attractive nucleus, and so they crowd in. Now, to be clear, when we're talking about electrons, they are still an enormous distance away from the nucleus and the protons in the nucleus. The analogy I think we heard in one video is that if the nucleus is the size of a spider, the electrons are traveling several soccer fields away. So just huge distances. Most of an atom is empty space as far as we're concerned. And so when I say that the electrons are close, they're not that close. But in comparison to other atoms, for this particular atom, the electrons are quite close. So the question is, what atom might this be? Well, you look at the number of protons, look on your periodic table. Which one has an atomic number of 10? Neon. So this represents neon, one of the noble gases. We know it's stable. It's got 2 electrons in the first orbital and 8 electrons in the second orbital. So it's a stable electron. Now let's see what happens if we have a less attractive nucleus. So take a look at this silly Haebel analogy. It always cracks us up. So this time it only has 7 protons. It's a little less attractive. And if I compare the two, let me go back to the first one. The electrons are closer to the nucleus in this case, and they're starting to get a little further away. They're not as attracted to that nucleus because it only has 7 protons instead of 10 protons. If we move further out and have a less attractive nucleus, then we only have 5 protons this time. Disgusting picture, I might add, and the electrons are further away. So compare the size of the atom. It's getting bigger because the electrons aren't as attracted to that less attractive nucleus. And then finally, the joke that Mr. Haebel makes, the least attractive nucleus in his analogy is our math teacher, Mr. Katzenmeier. So if he's really not attractive at all, the electrons aren't going to be near him, and they're going to spread out a further distance. But they can only go so far away. All right, so what we're talking about, as you move across the periodic table, as we move from lithium over to neon, lithium only has 3 protons. That's what Mr. Katzenmeier represents. And so it's not a very attractive nucleus. It doesn't have a strong positive pull for these negative electrons. But by the time we get over to neon, we have 10 protons, and those electrons are, they want to squeeze in really closely. Really closely, remember, is several soccer fields away. So it's not really, really close, but in comparison to the others. All right, so now you're going to probably want to pause this video again as you do some drawings. We're going to draw Bohr's model, and we're going to try to show their relative size using Bohr's model. So the first atom that we're going to draw is hydrogen. Remember, hydrogen has 1 proton and 1 electron, so it's just a single shell. The next one would be helium that has 2 protons and 2 electrons, and we're going to draw it just a smidgen smaller than hydrogen. That's because its nucleus is more attractive. Then we'll go down a row to lithium. Lithium is going to be bigger. Lithium has a stronger nucleus, a more attractive nucleus than helium does. However, the next electron had to be pushed out into the next orbital, the next shell. And so it's a step further away from the nucleus. And so although lithium's nucleus is a little bit more attractive than helium's, because we have to start populating a next orbital, it makes lithium bigger than either helium or hydrogen. If we go all the way to the end of lithium's row, we get to neon. It has the in that period, in that row, it has the strongest nucleus. So although it has 10 protons and 10 electrons, they're crowded in the closest. And so neon is the smallest in that row. Now we want to add another proton and electron. Well, neon is completely full. It's got 2 in the first shell and 8 in the next shell. So now we have to add another orbital. Boy, I wish this bubble could show my hands better. They keep getting cut off in this little space. So now sodium is going to be much bigger, and that's because we had to add an extra orbital. Technically, sodium has 11 protons and neon only has 10. But because that last electron is in a further out orbital, sodium has a larger radius. And then finally, argon is the noble gas. And let's see if I can get my picture out of the way. Argon is the noble gas in sodium's row, and it has 2 or 3 completely filled orbitals. So its nucleus is the most attractive in that row. And so in that row, argon is the smallest, and that's part of what makes it the most stable. The electrons are very, very attracted to that positively charged nucleus. All right, let's try finishing up these sentences. Lithium atoms are much bigger than helium atoms. So helium was number 2, lithium is number 3, because the last lithium electron gets added to a new orbital. Neon atoms, which are in the end of the row from lithium, they're actually smaller than lithium atoms because the neon nucleus is so much more attractive. It's pulling those electrons in. So as we go across and add more protons, the electrons start getting pulled in closer. All right, now let's go to a whole new idea. Up to this point, we've thought that protons equaled electrons. That's why that's the way that I've been teaching it. And that's true for what we call an atom. The word atom generally means it's neutral. You use the word ion if it's not electrically neutral. So atom means there's the same number of protons as electrons, like we see in this picture of the sodium atom. An ion, and you don't have a space to write this on your sheet specifically, so write it in between the slides. You have 4 slides on a page, write it in between or even below the slides. Okay, so ion is simply an atom that has gained or lost electrons. I would write that one sentence. I don't know if you need to write the others. If you listen, you might be able to not write the other things. Atoms gain or lose electrons in order to have a stable noble gas configuration. So take a look at the diagram. You've probably seen this before in junior high. Sodium has that 11th electron that's orbiting all by itself. It's completely not stable. Remember the difference between the terms neutral and stable. They do not mean the same thing. Neutral just means same number of pluses and same number of minuses, same number of protons and same number of electrons. If you have 11 protons and 11 electrons, then the charge plus 11 pluses, 11 minuses equals 0. That's neutral. A stable atom is one that has its outermost shell is completely full. Usually that's 8 electrons. And so if sodium loses its 11th electron, if it gets pulled away, then it has 8 in its outermost shell, which means it looks a little bit, in terms of its electrons, it looks like neon. A noble gas. Tricky. So a stable configuration means that the p sublevel is filled. You're going to start to get the hang that all the noble gases are 2p6, 3p6, 4p6, other than helium. Helium was 1s2. That one's a little bit different, but they're all p6. And now sodium, its last electron is in the p6. It doesn't have the next s electron anymore because it gave it up. Atoms will do whatever is easier, and that's very anthropomorphic, which means we're acting like it's a human. It's not at all. But is it easier to lose one electron or gain 7 in order to be a stable element? And the answer is it'll lose 1 electron. So in this example, calcium will lose 2 electrons rather than gain. Let's see, I'm trying to move me around here. Calcium will lose 2 electrons. Find calcium on your periodic table. It has 2 electrons in its outermost shell. It'll rather lose 2 electrons rather than gain 6 electrons. So when it loses 2 electrons, it's going to have an extra 2 plus charges in its nucleus, and it's missing a couple of electrons. So that's why we say it has a -2 charge. Chlorine, on the other hand, is just 1 electron short of being like a noble gas. So chlorine is going to do what's easier, and that would be to gain that 1 electron. So overall, it has 1 more minus charge than it does a positive charge. So we say it has a -1 charge. All right, moving on. Let's try a similar graph. This one I think I don't want you to actually write. I just want you to kind of do it in your head, and then I'll show you how to actually draw it. So same thing that we have on the bottom axis. So along the x-axis, the atomic number, starting with hydrogen and moving across. As the atomic number increases, what happens to a new concept? Ionization energy. I would put a little asterisk by this definition because I didn't make you write it out. And you need to know the definition. So ionization energy is the energy needed to remove an electron. If we were going to pull an electron off an element, I want you to think about, for example, I want you to think about sodium. Is it going to be easy or difficult to remove that last electron from sodium? Should be pretty easy because sodium wants to get rid of it in order to be stable. So it would have a what we call low, mosquitoes are coming out, a low ionization energy. A high ionization energy means it's difficult to remove that electron. So what is this graph going to look like? I hope that you can imagine that based on our previous diagram, it's probably not going to be a straight line one direction or the other. All right, so let's talk about it, and then we'll come back to the slide in just a minute. So let's make some predictions. I got to get my picture out of the way yet again. We have some possible energy units. It's just a made up term. So how much energy would it require to pull an electron off of a particular atom? So we give an example that hydrogen, it would take 13 energy units to pull its 1 electron away from its nucleus that has 1 proton. It's a fairly small atom, and its electron is very close to its nucleus. However, helium, the electrons are even closer. So if we try to pull, and it's completely stable, right? It's a noble gas. So if we try to pull an electron off, is it going to be easy, 5 energy units, or is it going to be difficult, 24 energy units? And I'm going to say this is going to be about the most difficult one to pull an electron off because helium is really holding tight to its electrons. Okay, so I'm just going to go through this really quickly, and we'll start labeling what would be easy to pull off and what would be difficult. You might be able to imagine that lithium, because its electron has moved out, is going to be fairly easy to remove its electron. Oh, sorry, give me a second to get my picture out of the way. I guess we went to neon next. Neon is a noble gas. It's very difficult to pull electrons off of neon. Let's take a look at lithium. I think that would be next. Nope, sodium is next. Sodium is very easy to pull it off because its electrons are quite far away from the nucleus. And so that's going to take very little energy in this particular example of all the different of the 6 elements that we have here. Sodium is going to be the easiest. It wouldn't be the easiest on the whole periodic table, but of these 6 choices. Okay, lithium is right above sodium. It's got that one that we want to pluck, but they are closer to the nucleus than sodium's 11th electron, which is a little bit further away. And then beryllium would be just a teeny bit more difficult, and that's because beryllium's nucleus is a little bit stronger than lithium's nucleus. It's a little bit more attractive. All right, moving on. So let's take a look at this graph, and then I'll help you go back and draw the graph that you kind of skipped at first. So which of these is most likely to be correct? Well, okay, hopefully you can look at this and go, it's probably not that, because that's not at all like the pattern we saw with the atomic radius. So it's going to be one of these. So let's think it through. I see helium and I see neon, and they're very high ionization energies, whereas here, helium and neon are low ionization energies. So is it easy or difficult to pull an electron off of a noble gas? Really difficult. So the correct answer is this graph. I know it's a dark slide, so maybe if you drew an arrow and said, this one, this is the first graph, is the correct graph. That's the one that would be the right answer. Now let's go back and look at what exactly your graph should look like. I don't need you to draw every single detail. I mean, you don't need to. Who cares what I need? You don't have to draw every single detail, but a few things I want you to pay attention to. As you go, the first ones you go up, helium should be at the top. Then you're going to go way down to lithium. Then you go back up to neon, but neon is lower than helium. Then you drop all the way down to sodium, and then the next one is argon, but it's lower than neon. So our mountains are getting a little bit shorter as we go. So pulling an electron off of helium would be the most difficult. Off of neon would be still difficult, and off argon would be the third most difficult. If you can draw that, then we're good to go. All right, so now let's complete some sentences. Sentence number 1, lithium has a lower ionization energy than helium. Look at where they are in the periodic table, because lithium's last electron is further away from the pole of the nucleus. Lithium has it has a more attractive nucleus. It's got 3 protons, and helium only has 2. But because lithium's third is further away, it's going to be easier to pluck it off. And so its ionization energy, it's what we call its first ionization energy, is going to be lower. Lithium also has a lower ionization energy than neon because neon has a stronger nuclear pull. Its nucleus is more attractive, so the whole atom is smaller and the electrons are closer to the nucleus. So it's going to be more difficult. It's so stable. It's going to be more difficult to pull an electron off of neon. All right, and then you might notice there's a typo on your note packet. This says lithium on your note packet, so cross that off and write neon. Finally, this one's going to take a little bit of writing on your part. Neon has a higher ionization energy, first ionization energy, than argon. Neon is right above argon. Argon is also a noble gas because this is kind of a difficult concept, so let's write it down and then we'll make it make sense. Argon has a stronger nuclear pull. Argon has more protons, but the inner electrons of argon shield the pull of that stronger nucleus from the outer electrons. So they block the outer electrons from some pull of the nucleus. Go ahead and write that down. Pause me if you need to, and then I'm going to explain it right now. So in Mr. Haebel's inappropriate analogy, we had that really attractive nucleus, and the electrons were crowded around it. Now imagine that there's another shell of electrons. They would have trouble seeing that really attractive nucleus because the electrons are so crowded around it. And so they don't experience the attractive pull. This is an analogy, not real. They don't experience the attractive pull quite as much as the inner electrons would. And so the electrons of neon, they're close to that attractive nucleus. The argon electrons, the nucleus is actually more attractive, but they're further away and they get shielded by the inner electrons, and so they don't get pulled in as tightly. All right. Last thing, there's just 2 more slides to go. Hopefully I can get this in under 30 minutes. So it says, what trends, let's see if I can move me out of the way yet again. What trends do you notice? First of all, on your note packet, the highlighted yellow staircase didn't really turn out. So pause me and get that highlighted yellow staircase. I really want you to make sure that you can see that in your notes. Okay, I'm going to keep talking. As I look at this data table, what's going across the top is one period or row of the periodic table. It starts with sodium. Remember, sodium has 11 protons and 11 electrons. It's got that one electron, super unstable. Goes all the way across to its neon gas that's in the same neon gas. I said it again. Noble gas that's in the same row, and that noble gas is argon. All right, so let's take a look. These are called successive ionization energies. It means the amount of energy necessary to pull off the second electron or the third electron or the fourth electron. So what we should see are lots of patterns. First of all, every time you pull off an electron, it becomes more and more difficult to pull the next one. And that's because in comparison, the nucleus is getting stronger. If I start with sodium and it has 11 protons and 11 electrons, and I take one away, now it has 11 protons and 10 electrons, so the nucleus is more attractive. And if I pull off 2 electrons, now it only has 9 electrons compared to still 11 protons. So every time as we're going down, as we pull off one electron after the next, it's going to be more and more difficult. Likewise, as we go across, there's a little bit of a pattern. Generally, it gets more and more, and there's reasons we're not going to go into, but generally it gets more difficult to pull the electrons off, and that's because the nucleus is getting stronger as we go across the periodic table. Now, the part that we really need to see is the yellow part in particular. If you have a chance to really look at this data table, pause me, look at it, and see if you can figure out why. The yellow is identifying huge jumps in the ionization energy. Pulling one electron off of neon is fairly easy, but pulling that second electron off of neon is very difficult. That's because neon already looks like a neon gas after we take one off. Oh my gosh, I said it again, a noble gas. Blah, blah, blah. Sodium looks like a noble gas after we take one electron. And so it doesn't want to give up the electron that's number 10 because it's stable. And you have to fight to pull off that electron. But magnesium, it has 2 electrons in its outermost shell. So it's fairly easy to take off one. It's a little bit more difficult to take off the second, but super hard to take off the third because it looked like a noble gas when you removed the first 2. Aluminum, you can take away 3, and then it looks like a noble gas. If you try to take away the 4th, it's much more difficult, and so forth and so forth and so on. Argon doesn't want you to take off any because argon was stable to start with. All right, so things that you could write down. The successive ionization energies increase with the removal of each electron. I would write that one sentence down. However, there are occasional huge jumps in ionization energies highlighted in yellow. You do not need to write that down. Last thing. There's a lot here. I'm going to go through them quick, and I'll tell you the one thing I think you should write. It is increasingly difficult to remove electrons because the pull of the nucleus is growing stronger. It's more attractive. When one electron is removed from silicon, there we go, the number of electrons is 13, but the number of protons is still 40. So it's a stronger positive pull. When a second electron is removed, the number is 12 electrons, but the protons is still 14. The huge jump right here occurs when the atom has achieved a noble gas configuration. When a 4th electron is removed from silicon, the number of electrons is 10, the same as the noble gas neon. But if we try to remove the 5th one from silicon, it's going to fight us tooth and nail because it was stable and it wants to stay stable. All right, everybody, that is the end of the notes. Please let me know if you have any questions.